This should be the last video for section 4.2. So we completed examples 2 and we were supposed to look at example 3 now. So it says define t from p2 to r2 by p of p is any polynomial, is equal to p of 0 and p prime of 0. So this is a 2-component vector, so it is in R2, and the entries in the vector are p of 0, means in the polynomial p you will plug in 0, and then the second coordinate is p prime of 0. So you will take the derivative and then plug in 0, and whatever you get, that will come in these places. So first question says show that T is a linear transformation. So now we are in general, we have to show that it is a linear transformation. So for linearity, remember these two steps or these two conditions that it has to satisfy. One is that if we take two polynomials from P2, by the way, I hope everyone remembers that P2 is all the polynomials of degree 2 or less. So and note there that the P2 has dimension 3 because standard base for P2 is 1t square, whereas R2 is of dimension 2. So this is of dimension 3 and this one is dimension 2. Anyhow, so we pick two polynomials in P2, so I pick P and Q. If I add them and then I take the transform, so I have to show that the result is same as if I take the transform of each of those two polynomials and then add them. And then second is that we have to show that if I take the transform of a scalar multiple of a polynomial, then it should be the same as the scalar times the transform of the polynomial. Or you can do it in one go. Instead of doing those two separately, you can show this, that k times pt plus qt. So if you take the transform of that, it will be the same as k times transform of p plus the transform of q. Here I am taking this second condition that I wrote here. So let p and q be in P2 and let k be a scalar. Now remember, it has to be a non-zero scalar. To show p, k, p plus q is equal to this is what we have to show. But first we start with what p looks like. So it will be a polynomial of this type, a0 plus a1t plus a2t squared, and the qt will be b0 plus b1t plus b2 squared. So now when I find k times p plus q, I get this result. So I have k a sub 0 plus b sub 0 plus k a sub 1 plus b sub 1 times t plus k a2 plus b2 times t squared. Now if I take the derivative of that, the constant term, the first term will be 0, and I will be left with ka1 plus b1 then plus 2 times ka2 plus b2 t. So the t is gone from here, in this case, and the t square became t and the constant became 0. So now what will be the image of this polynomial kp plus q? It will be when you plug in 0 in the polynomial. So if you plug in 0 in this polynomial here, so this is 0, this term is 0, this term is 0. So you are only left with k0, k0 plus b0. And when you take the the prime of 0, the prime and at 0. So the prime is, we found the derivative in here. So only this term is 0. So first term is left, ka1 plus b1. So this is what I have. So I can write this as ka2, ka0, ka1, and then plus, what to say, so I can write it like this vector plus this vector, or I can just leave it as it is. If you notice, this can be written as ka0, ka1 plus b sub 0, b sub. So if you notice, this is what k, so k times a0, a1 plus b0, b1. Now this is t of p, and this one is t of q, and the k is over here. And this is what we wanted to show. Or you can leave it here and then go to the right hand side. Go and try to find the KTP plus PQ. And you will see that you get the same answer that I have shown you. So this is how you show the linearity. The second part is we have to figure out what is in the kernel of T, and then what will be the in the range of T, or what will be the range. So first, for the kernel of T, the kernel of this transformation, basically we are looking at the null space. So what is the null space? That all the vectors in P2, or all the polynomials in P2, which are going to be mapped on the 0, 0 vector in R2. Remember that because we are talking about the standard addition and scalar multiplication here. So we are going to get a 0, 0 will be our identity vector. So I write this mathematically. So we want to find out P, or a polynomial P, such that when you transform P, you get the 0 vector. So here I have the 0 vector, 0, then vector rotation, and in here it is actually this vector 0, 0, because we are in R2. So we want, in other words, we want this quantity to be 0 and this quantity to be 0. What does that mean? It means if P look like A sub 0 plus A1t plus A2t squared, then P of 0 will be 0, and then P prime of 0 will be A1. So we want this to be 0, 0, which means A sub 0 should be 0 and A sub 1 should be 0. So what are we left with? We are left with A2t squared. The polynomial, all the polynomials which have only the t squared term, any number being multiplied by it, you can in general say P t is equal to A t squared. So all the polynomials which are of this type will be in the null space, or will be in the kernel of T. That's what I wrote here, the set notation. Now for the range of T, so we want to see any vector CB Why am I writing here A, B, C, B? Well, we can do it with A, B. Any vector A, B such that, but now I have to change the condition because it will mean A, B belongs to R. So A and B are real numbers, and the situation is then the polynomial should have been. What is that polynomial, and what is the pre-image of AB? So what the polynomial is, so it means all polynomials P of t which are looks like this. So A was, remember, the first P of 0 gave us A, so A has no variable, so A plus B t and plus ct squared. So will there be a polynomial of this type for any values here? Yes. So it means the range is the whole R2. So, but what are the basis vectors? From here you can say the basis vectors of this system are A into 1 0 and B into 0 1. So because we are saying the range is the whole R2, means that the T maps P2 onto R2.